because we're talking about linear operators, I usually put the hat on the representation and no hat on the operators. So this is a hat here, there's a hat here, there's a hat here. Yeah, good. So, yeah, good. I have a hat. Yeah, so again, you act on a cat. This is now your basis cat, the tensor product cat. And it gives you back a cat. And that's the most general case that you can get in a tensor product space. And then finally, let's think about, any questions at this point? Okay, so now we're going to answer Weihao's question, okay, which is this a tensor? And the answer is yes. Right? All of them are tensors in the following sense. This is a tensor, that's also a tensor. In the following sense, we're going to study what happens when you change your basis, right? Just like the way we did it for one vector space, we implemented it through a unitary transformation. Okay? And so now we're going to do the same thing. So you can probably guess, if you're going to change your orthonormal basis, you're going to do it vector space by vector space. Okay? So you don't need to write down a giant multi-index object like that. But what you do need to do is you need to implement. Maybe I'll do it here. Yeah, actually, let me just erase the whole thing first. So, So we're going to do a change of basis. Sorry, back one. And so if you're going to change your basis, you just need to change your basis at for each vector space. So what does that mean? Well, it means you're going to take, I will have to have a unitary operator, but again, because I have n vector space, I need to label my unitary operator IU. What does IU do? It takes the I, it takes the vector from the I vector space. Okay, so this is the Li basis vector from the I vector space, let me describe it, from Vi, okay? And it's going to give me, say, Li prime. Remember, that's what we did. We took the I, previously it was U acting on I, gave me I prime. You guys remember this. So it's the old basis, and it gives me the new basis. Okay? And so what you want to do is you basically want to act, because you're just changing it slot by slot. So all you need to do is to act the tensor product of these guys on a vector, on a given vector, and that will give you the new basis. Okay. So let's do it. So suppose I have a vector which I'm going to call V. Doesn't really quite work. Yeah, let me just call it V. Okay. So this is going to be V hat I1 all the way to IN, and then I1 all the way to IN. And now what I'm going to do is I'm going to insert a complete set, a completeness relation involving the new basis. Okay. So yes. So what it's going to look like is going to look like I prime 1, I prime 2, all the way to IN. And then change my marker. And then I1 prime. So this is the cat. The completeness relation is, remember, this guy. But now our cats and graphs are this more complicated object. Right? So I need to do this. But these are all primes. Right? So this is the new basis, and it's going to act on the old basis, which is this guy here. And what do you get? You get that you get sum over, so now there's a sum over both the i's and the I primes. Okay, and this is just shorthand for saying that I need the sum of all these indices and these indices as well. But now, when I act on that, I get the following, right? I get V I1 to IN. And now these are numbers, because I act this guy on this guy, the second guy, and the nth guy, and the nth guy. So I get the following. I get I prime 1, 1, acting on I1, 1, all the way to I prime n, acting on IN. Okay? And then the basis vectors are now the new ones over here. So I'm going to put a parenthesis around here. And write down I prime 1, 1, all the way to I prime n, n. Okay. Now, let's write it in terms of the use. Okay, so what the use tell us is that if I act on, I should use this language over here. If I act on, what symbol did I use? I. If I act on I, maybe I should use different symbol. So I say L, L, L. It gives me the new basis, the new prime basis, right? So if I take the matrix element in the O basis, so I think I screwed up somewhere. I shouldn't call them the same symbol because it's very confusing. What I mean to say is that I don't mean that these are the same numbers. I mean to say that these are, so I better call them J's because these are different. I'm sorry. So this is J, 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 J. Okay, again, let me just correct myself. I don't mean to say that these I's are the same as these I's. In this case, I mean the same, right? This is the same I as this I. It just happens that this is the I basis in the O basis. This is the I vector in the new basis. But here I don't mean that. This sum over J is independent of the sum over I's. So I'm sorry, this is a mistake. So let me just fix it. This is J's, J's, and these are I's. No, these are J's. Okay. Yeah, okay, now we're back in business. So if I apply J, L, L on this operator, so again, this is the Ji component of this unitary operator in the Lth vector space, right? So let me write that down. This is now the Lth unitary operator acting on the Lth vector space. Its matrix element is the Ji component. That's what I mean here, right? And this is given by the overlap between JLL and ILL. Okay. Prime. This is new, this is old. Okay. And now this, you see that that's exactly the complex conjugate of this guy. Okay. That's the complex conjugate of this guy. And you may recall that we said this before when we did the case for the single vector space, that the upper indices, the way we define U, the upper indices transforms like a U dagger, and the lower indices transform like a U. If you guys remember our discussion over there. And that's what's happening here. So what we have is that now V is given by, let me write down the basis first, J1 prime all the way to Jn prime. And then for the components, you have these guys contracted with V, but these guys are in fact these guys are in fact U dagger. Like this way. So one U dagger. J1, I1, and then 2 U dagger J2, I2, all the way to the nth guy, contracted, all contracted with that guy, that V I1 IN. And therefore, you can call this, you see, remember that what is this guy? This is the components of the tensor V, of the vector V, that are in the O basis. But now we have the new prime basis, so we should call this V prime, V of J prime 1 all the way to J prime n. Or if you like, you can put a prime on the V. But I often put the prime on the indices, so let me just continue to do that. Okay, so this is the definition, because the components, the coefficients of the basis vectors are what we mean by components. Okay, so but if you compare this with this tells you the following, right? So we have a tensor transformation group. Now we have a which is the following. If you take the new basis, then you want to know what is the, so this is the new basis, the new components, components in the new basis, right? And you want to know how to run it in terms of the old basis. Then first you want to know what are the matrix components of your unitary operator that will change your basis for you. And then you go ahead and say, okay, so this would just be the first guy, dagger, contracted with your old component. Let me write it down over here, V I1 all the way to IN. And then 2 U dagger J2 I2 all the way to N U dagger Jn IN. Okay. Just by comparing this guy and this guy. So you can probably guess what will happen for the lower indices. Oh, it's your homework problem. I did your homework for you. Well, that's what happens all the time. Do your homework for you. Okay, well, I'm a bad professor. That's half the homework, so you do the rest, okay? So you'll figure out how to do the one for the brass, right? But I already did the homework for you. So you have to figure out how to do it for VI prime. And so this is for the brass. Okay, how is that related to the O basis? Let's call this the J's and the I's. Okay, so you figure this out. Yeah. Any questions for me? So the answer to Wayhouse question is yes. This is a tensor. The tensor is not restricted only to differential geometry. The tensor is just any components of a vector, essentially. A vector in a general sense. This is a vector, right? It has a multiple, it's a tensor product of multiple vector spaces. But even if you have one, it's still a tensor. Why? Because the tensor is defined by its well-defined transformation properties. As long as there's a defined change of basis, when you go from one basis to the other, you would call it a tensor. Except that the change of basis in differential geometry means something slightly different from what we mean here, right? Because in differential geometry, these bases are either derivatives or they are infinitesimal, the dx, dy, and so on. Right? So that's a different meaning. But in some senses, it's more general, right? Because I'm not specializing to what these cats are. Okay, so in some senses, it's more general. Yeah. Any questions? Okay, so next time we'll start doing continuous operators. See you guys on Monday.